And on that note, I would like to switch to Amy. Amy, being a professor at the Brown University, you all read her profile, so you know who she is. Amy, please enlighten us on means of transport and anything else that you need to talk to us about. Here you go, ladies and gentlemen, Amy Greenwald.
Thank you so much, JJ. Thank you everyone for being here. Thank you for the kind introduction. Yes, about means of transport. So you've all read my profile, so you know that I have lived in Amsterdam, not far from JJ, and I have also lived in Japan. And the most prevalent means of transport in these two places is not the same. Of course, the Dutch are famous for their bicycles, whereas in Tokyo, most people are traveling by train. And the fact that people are using these means of transport and not, for example, using bicycles in Milan is not an accident. It has to do with the mechanisms that were designed by those cities for their commuters or for people living in the city more generally. So in particular, the Dutch have invested heavily in bike lanes, and of course the Japanese in trains. So you see that the choice of mechanism that they instituted in these cities has really affected the decisions that are being made by the people in the city. So this is a mechanism design where you have the participants in the mechanism actually making informed decisions based on the mechanism and based on also their own interest, their own, what's best for them given the mechanisms available. And again, the bike was not the best choice in the center of Milan for JJ. So I will talk to you today about mechanism design. So for example, transport choices or where to invest in transport by cities. And more specifically, I'm going to focus on the games that are played when you design a mechanism, when you choose a mechanism, when a city decides on their transport system, that's creating a game. And there are then players in the game, namely the people who live in the city, who kind of, they best respond to the mechanism and to what everybody else is doing. So they play a game inside of the mechanism. So we're talking about two things here: how to play the game that is created by the mechanism, and then also how to optimize the mechanisms themselves. So I'll be talking about this joint work with Enrique Ariane Figuera, Cyrus Cousins, and Yasser Mohammed. All right, so I've already told you a bit about what a mechanism is and what mechanism design is. Here is another example, this picture at the bottom, of a mechanism. This is a voting mechanism. So generally, when a government or anybody is designing a mechanism, they have some objective in mind. So in the case of voting, the objective may be to, elect the candidate that the people like the most, for example. So they set up some kind of system, such as plurality voting, where everybody votes for one candidate and we count up the votes and whoever gets the most votes wins. That's a system. And then we want to evaluate whether the system that is being set up is a good system or not a good system. So that is the mechanism design problem. And so actually in the States, we don't have quite plurality voting. We have an electoral college. So I'm not sure if people are familiar with the Electoral College, but there are representatives from every state that actually do the voting for president on behalf of us. So it's not just that my vote gets counted directly in the evaluation of who's going to be president. It's actually that then a representative goes to Washington, I guess, and votes on my behalf. So the Electoral College actually does not end up necessarily electing whoever got the most votes. So this happened, for example, Hillary Clinton got 3 million more votes than Trump, but she was not elected president because the Electoral College is an intermediate mechanism that's doing its own thing. And so we can ask the question whether the Electoral College is a useful or a good mechanism. Is it leading to a desirable outcome? So people will have their opinions one way or the other on this question. So that's an example of a mechanism, and we can ask whether it's doing the right thing. Many mechanisms abound, right? Transportation is, the systems we have are some kinds of mechanisms, and here I have a few slides, one in education, one in healthcare, one in economics, on lots of mechanisms that are everywhere. So school choice is a mechanism that I participated in here in Providence, Rhode Island. When I was sending my children to school, I get to list the schools that I might be interested in sending my kids to. And the reason that school choice was invented is because in the States, property taxes are used to fund schools. Now, if you have property taxes as your primary means of funding schools, then you have the adverse effect that very rich districts, very rich neighborhoods end up with very strong schools, and poorer neighborhoods end up with not as good schools. They have less funding. So school choice was designed to let kids go to another school in their district, maybe not the school that's right in their neighborhood. And the goal, of course, is to improve student learning outcomes. But again, there are potentially adverse effects of these mechanisms. So for example, in Providence, we ended up with people choosing all over the city, so that I'm living, in one part of wherever I'm living, my neighbors may end up going to all different schools. And so we end up sort of splitting up the community, and we end up with very high busing. All of a sudden, the buses cost a lot of money because everybody has to go this way, that way, and the other way. So you have some particular outcomes you're aiming for, but of course, then based on the choices that people make, you may end up with some adverse, not necessarily what you are hoping for. So, and again, another interesting feature here is that when I'm going to list the schools that I prefer, how do I do that? How do I think about that? So once they set up this mechanism, I have to play a game. I have to think about my preferred schools, but do I really just list my favorite school, my second favorite school? Do I really just list them in order? I didn't do that. I have to think. Well, this preferred school of mine is very, very popular. And, it's not very likely that my kid is going to get in. I mean, there's a lottery, however the decisions are made. It might be too popular. I might not get my first choice. So instead, maybe I'm better off listing my second choice as first, popping my second choice after first, because maybe my chances of getting in are better. So that's the game that I have to play when the school choice mechanism is created. And there's a game that's been created by kidney exchanges. I won't talk about it here now, but it's the same sort of situation where the hospitals can potentially game the system. And another example, which I will go into detail in this talk, is auctions. Auctions are another kind of mechanism. And again, it would be nice if you didn't have to game the system, but ultimately in real world auctions, they are ultimately games. So these three examples that I mentioned, by the way, school choice, kidney exchanges, and optimal auctions, these examples are very important and have beautiful, elegant theories designed around them, for which Nobel Prizes have been awarded to the designers of these mechanisms for some idealistic scenarios. The problem is, the school choice issue that I was just mentioning to you about me having to game the system, that's not part of the, that's not necessarily in the Nobel design. There were some simplistic assumptions that made it so, hopefully you wouldn't have to game the system. That's sort of the ideal if you didn't have to game the system, but in the real world, most of these designs end up with some opportunity for gaming. So this is what my talk is about. It's about that we have a mechanism design, and inside of it, you really have to play a game. There's a game that shows up. As much as you would wish that there weren't a game, at the end of the day, there is a game. So in the optimal auction design, there was a very clever solution to designing. So here, optimal, by the way, optimal can mean whatever you want it to mean in a mechanism. It could mean, optimizing for student learning outcomes. It could mean minimizing bus costs. It could mean whatever the designer wants it to mean. Here, for optimal auctions, it means making the most money. This is for the auctioneer to bring in the most revenue. And so the clever solution here that led to the Nobel Prize was to introduce something called a reserve price. In order to bump up payments, introduce a reserve price, and you have to bid above the reserve price to even be in the auction. So if you don't beat the reserve, you're out of the auction. And this has the effect of potentially bumping up revenue because everybody has to, make sure that they're above the reserve to get into the auction. So, but at the end of the day, as I said, the real world auctions are not as simple as the one that was analyzed here for this producing the optimal auction. That was an auction for just one good. But the kinds of auctions that we see in the real world, here's an example, an advertising exchange. So if you're not aware, all those ads that you see whenever you go to, I don't know, the New York Times or whatever paper you're reading, or wherever you go to any website, all those ads that you're seeing, those ads are being sold in auctions. So I've been an active participant in the trading agent competition for many, many years, and more recently in the negotiation agents competition as well. And so I've been building agents for these kinds of setups where in this particular competition, we were actually simulating an advertising exchange. So an advertising exchange is a place where when I go to the New York Times, my identity is, they know that we have a 50-year-old woman from Providence, Rhode Island, and, here she is at the New York Times. Who wants to show her an ad? And so now these bids come in on me to say, oh, she likes biking, or, she likes, I don't know, canoeing, or whatever I might like. And, let's show her various different ads for things that we think that she might be interested in purchasing. And so I am basically for sale. And in this competition, we had a bunch of different ad networks. And the ad networks were not representing just one advertiser, not just the bike company or the canoe company, but they were representing a bunch of different advertisers. So maybe they're representing, car companies and bike companies and this and that. And so the ad network is bidding for the users as they show up. So the competition here, the game here, was played among ad networks representing a bunch of advertisers, and the simulation had the users showing up and us bidding to hopefully, get the users to show up and to click on our ads and ultimately buy the products if you won the auction and were able to show them your ad. So again, this is a game, but it's a mechanism. There is a mechanism that's sort of set up here that is defining the game. And in this mechanism, we had a bunch of different kinds of market segments. So the market segments were who were the users that were showing up to the ad networks. So we had males and females. Again, this is a simulation. We have males and females, we had rich and poor, and we had young and old. So there were 8 different market segments. So ultimately, there were 8 kinds of auctions that were running. So we actually set 8 different reserve prices. So there were 8 reserve prices that were defining the mechanism, and then the ad networks had to figure out how to bid in these simultaneous 8 auctions. Okay, so that is the advertising exchange game as set up by a mechanism. And we went ahead and studied the mechanism design problem here, which means studying how can we optimize the reserve price, assuming that these ad networks are all playing a game amongst themselves that's defined by the reserve price. So I hope that's clear. So we have a mechanism design problem. In this case, it's setting reserve prices, and that mechanism ultimately creates a game that's played by, in this case, the ad networks. So it's the same sort of thing when your city is setting up its transport system. It invests a lot in trains, and now there's a game to be played among the people who live in the city. Should we take the trains? Well, in Tokyo, they all take the trains, and then it's very crowded on the trains, but then maybe somebody says it's too crowded on the trains, I'm going to take the bicycle, right? So they're doing something different. They're playing the game, however they're playing the game, but it's all in response to the way the mechanism is designed. So the question I'm asking here is kind of twofold. I mean, one, I have to figure out how the game is going to be played. So once the mechanism is designed, how are they going to play that game? And that means we're going to think of that as what is the equilibrium of the game that's defined by the mechanism. And then we have another optimization problem outside of that game, which is now let's try to optimize the reserve prices. So in this case, we're going to try to optimize 8 reserve prices. So this is a hard, big optimization space. So we're optimizing 8 reserve prices, and inside we're simulating a game being played by these ad networks. And again, you can think of that analogously to the transport system in your hometown. So this is a competition I've worked on for many years. This is future work, supply chain management, the competition I'm working on now. So the idea here is to kind of move negotiations among in the supply chain from people who are taking each other out to dinner. Well, we're not doing that anymore, but who are negotiating with, people that they know or have known for a long time, moving that into the agent space so the negotiation happens through agents. And again, we have to design a mechanism. The idea that this game is being sponsored by NEC in Japan. They're hoping to build a platform where we can see agents negotiating throughout the supply chain. And the question is how to design the best negotiation mechanism. And, we have to think about what the objectives are. Of course, NEC wants to make some money, like eBay, for example. They designed an auction mechanism and they want to, make some money for themselves. But of course, you also want a platform where people are going to participate. People are going to be active. You want to have volume on that platform. And so you have to balance these things in designing the mechanism. Anyway, this is future work, how to design negotiation mechanisms, but ongoing work now, we've started. All right, so I am now going to start to dive into some of the details about how we actually solve these games. I'll warn you, the talk has a lot of technical content. I can show you some, well, you'll see it, but there's some very mathy slides. I won't go over those in detail here, but I will post them so they're available for you to read at your leisure. So first of all, we're going to analyze this multi-agent system using game theory. So if you are not familiar with game theory, we'll have like a 1-minute primer here. But again, I'm showing you the prisoner's dilemma on the right. This is the most famous game. Please go look it up. It's a lot of fun to think about and to try to analyze and see what's going on. So what's a game? A game has players. The players have strategies, and they also have objectives. So they are going to act strategically to maximize their objectives, but not just kind of in isolation. They think about what other people are doing. That's what I did in the school choice problem. I had to think about, well, too many people are applying to that school that I really like, so you know what, I better apply to some other school. So we're looking for an equilibrium outcome where everybody is happy with their choice, everybody is happy with their decision relative to what everybody else is thinking about. So that's an equilibrium in a game. But we are particularly concerned in this work with what I call simulation-based games. So this means that I cannot write down the game in this little box like we've done here for the prisoner's dilemma. This means that a complete analytic description is not available. I have to run a simulator, which is what we were doing in those games that I was talking about. But running that simulator is not cheap. It is expensive to run that simulator. So we will run it, but we'll try not to query it too many times if we can avoid it. That's the goal in a simulation-based game. So now we'll look at empirical game theoretic analysis, which means the analysis of these simulation-based games, which means, again, that we try not to ping the simulator too many times. Empirical game theoretic analysis has been going on for at least a decade, where you basically empirically estimate the game and compute the equilibria of the empirical estimate. So there's one key assumption that we should mention here, and that is that in general, equilibria are very hard to compute, notoriously difficult. But we are assuming here that that is not the hardest problem. The hardest part of our setup is actually running the simulator. Querying the simulator is more expensive than computing the equilibria. So I'll say that, you know, it's a little bit like NP hard problems. Like NP hard problems, maybe we should shy away and we should not even think about them. They're just too hard. But at the end of the day, of course, they show up everywhere. So we have SAT solvers and they're doing great things to solve NP hard problems, even though, of course, they're NP hard. So it's kind of similar here. There's a web page of game solvers available, and I don't know, in 20, 50 years, maybe we have, you know, the power, the computational power to really to solve these games, even though they fall into complexity classes that make them notoriously difficult. Okay, so again, more expensive to query the simulator than to compute equilibria. So here's the basic outline. What we're going to do now is we're going to talk about approximating and then learning equilibria in simulation-based games. So here's a famous game, rock, paper, scissors, right? 2 players, 3 actions each, rock, paper, or scissors, and the rules are shown by this diagram. Hopefully everybody has played this game and know how it goes. So again, it can be written like the prisoner's dilemma was written before in this tabular format. So here's showing that, you know, rock beats, I'm pointing to my screen, that doesn't help you. Rock beats paper, and so therefore, no, sorry, rock does not beat paper. Rock loses to paper, and therefore we have a -1 in this cell because we are showing here the gains of player 1. All right, and here's the whole picture of all the payoffs that you find. All right, and then we have this famous excerpt from The Simpsons. Right, so you know Bart, he's a really smart guy. So he's got his strategy all worked out, right? He's playing rock. That's what he's doing. So is that a good idea in this game? Well, if we had time, we would take a poll. I'll just let you think on that. Do you play rock? When you play rock, paper, scissors, do you play rock always, like Bart does? Presumably you don't. And why don't you? Because if you do, then your sister Lisa will beat you every time, as shown in the previous table. Okay, so playing rock all the time is not going to work. What about playing scissors all the time? Is that going to work? No. What about playing paper all the time? Is that going to work? No. And so what does that tell us? It tells us that there is no what's called pure strategy equilibrium. There's no like single action that you can do that's going to be part of an equilibrium. What do you have to do in rock, paper, scissors? You basically have to play randomly. You have to just try to trick your opponent into, you know, not knowing what they're going to do. So you randomize instead of playing a pure strategy. And we have instead what's called a mixed strategy equilibrium. Okay, so here's where the math comes. So I'm going to skip it in the interest of time, but we have here formalisms for everything that I've been talking about. But what's important here is to know that the pure equilibria might not exist, whereas the mixed equilibria always exist, and the pure, when they do exist, are a subset of the mixed. All right, so that's our basic game theory introduction. We also have an approximation framework. So what is an approximation framework, or how is ours going to work? What we're going to think about here is one game being an approximation of another one, when, if you look at all the boxes, so we have all the boxes in of a table like rock, paper, scissors, or prisoner's dilemma. So we have this, and again, we can't write it down for simulation-based games. It's too big and too complicated, but you can still imagine it, right? And so we have these tables, and so imagine two tables that have exactly the same structure. And then the idea of an approximation is that if we look kind of across the tables, so we see like everything in the first row, everything in the second row, in the third row. If we look across the tables, all the entries in the two tables are within epsilon of one another. Okay, so one game is an approximation of the number of the other if when we look at all the corresponding entries, they're all within epsilon. Okay, so that's what we mean to have an approximation. So when we have an approximation, we have a very nice result. When we have that one game is an approximation of another one, we have, let's look here at kind of a number 2. Okay, so number 2 tells us that the equilibria of the game are all contained within the equilibrium of the approximation up to a 2 epsilon error. So we have an epsilon uniform approximation, and that will give us this result with 2 epsilon error. So what does this mean? It means that we have perfect recall. Everything that's an equilibrium in the true game is a 2 epsilon equilibrium, so an approximate equilibrium in the approximate game. So that's the first direction. And in the second direction here, we have almost perfect precision, approximately perfect precision. It tells us that we don't have too many false positives. So there are not too many things showing up here as approximate equilibria in our approximate game that are not also approximate equilibria in our true game. So that's the second inclusion here, approximately perfect precision. So this is just telling us that our uniform approximation theory gives us a nice recall and precision result. So this means that if we build these approximations, we can find approximate equilibria. And there's the proof for you to enjoy on your own time. Okay, so next we want to talk about learning these things. So how are we going to learn them? So we are going to learn them by pinging our simulator. Oh, isn't that a beautiful slide? Again, it's for something for you to figure out on your own time later. But the Hufting bound is a very key part of this and very important thing for you to make sure that you do learn about at some point. So we are going to keep pinging our simulator and trying to find out how to fill in all of these boxes, like what numbers are going in these boxes. What the Hufting bound will tell us is that if we have some desired accuracy, so desired epsilon, and moreover, we have some probability, 1 minus delta, with which we would like to see that accuracy, it's going to tell us how many samples, that's this M down here, how many times do we have to ping the simulator so that we can get the accuracy with high probability that we desire. So that's what these kinds of bounds are telling us, and we will use them in order to learn a uniform approximation of our game so that we can have the precision and recall result that I presented earlier. So I don't think I'll really have time to go into the learning algorithms, but I do want to tell you that the Hufting bound gives us a uniform approximation, and we have other algorithms which are more efficient in terms of sample efficiency, so fewer samples for the same guarantees. They use non-uniform approximate. They non-uniform bounds and create a non-uniform approximation. And here's some graphs showing how those work. They work well. They're great, and they're ongoing research. This is actually old results from a year or so ago. We have new algorithms that are even making more frugal use of data. So we're doing even better than is shown here. All right, let me return to the game that we're playing, because what we did was we used this methodology to play in this game. So as I told you, I've been participating in trading agent competition. So I have developed agents that can play this game. So I won't be able to describe them today, but we'll call them WE and WF. WE stands for Walrasian equilibrium, and WF is a waterfall algorithm that we designed where kind of go down. Anyway, so I would be happy to share resources so you can read about these algorithms. But the point is that we then played this game using our heuristics. We played this game as designed using WEs and WFs, trying to then, calculate what the empirical equilibrium would be. The empirical.
JJ here. Sorry to interrupt. We agreed that I would interrupt you to give you a little warning. Could you finish within a minute or 5?
Within 1 minute?
5 minutes. You have 5 minutes left.
Okay, 5 minutes. Yep. I'll do it. Okay. All right, no problem. Thank you. Right. All right, so we're going to play this game. And so we're then going to think about trying to compute an equilibrium in this simulated game. So we did not do this for Nash equilibrium. We could have, but we happen to have used sync equilibrium instead. So what I'm showing you here is what's called a best response or a better response graph. What it says is that this is a 1WE and a 7WF setup. So we had 8 agents in this game. And this says that one of these WFs would rather be a WE, because here we have a 2WE and a 6WF. So this guy decided to switch his strategy to another strategy. The reds are the sync equilibria. So we're looking at a graph that says, if I were playing this, I would have rather played that. And we can sort of, walk along the graph to get to where the equilibria are. So with that in mind, I now want to think about designing the mechanism. So what does that mean for this game? Again, designing the mechanism meant trying to choose the reserve prices. So how are we going to do that? We do that with a technology called Bayesian optimization. Bayesian optimization is an amazing technology. It works incredibly well. It is useful for black box optimization. So this means that we don't have a closed form. We don't know exactly the form of the function we're trying to optimize, which is exactly the setup we have here, because we have a simulation of a game and we want to choose the reserve prices so that in our case, actually, it was to maximize revenue. I don't know if I said that, but trying to get as much revenue as we possibly could. So we have an objective to achieve, which is to maximize revenue. But the reason it's a black box optimization problem is because inside that objective, we have to go ahead and figure out, once we pick our thetas, which are the reserve prices, that defines the game. We then have to find an equilibrium of that game. And then we have to figure out the revenue associated with the equilibrium of that game. So it's a very complicated optimization problem. We used Bayesian optimization. We tweaked it a little bit based on the noise that was coming out of our learning algorithms, which I'm showing a picture of here. We basically had to take our noise, which has this blue structure, and fit it to this Gaussian. All right, now with that, we were actually able to optimize the reserve price. So I'm showing you here a picture where we're seeing that Bayesian optimization found an optimal reserve price. Now, this is only for one. I told you there are 8 markets. This is just for one, because I can't show you 8 dimensions. But in this case, it found it after searching only 13 reserve prices. So looking at this continuous space of reserve prices, after 13 choices of running this incredibly expensive machinery inside, right? Because again, we have to find the equilibrium for that reserve price and then, figure out where we're getting the highest revenue. It was able to make choices. What reserve prices should it investigate so that it could, after 13 tries, find basically the optimal, which is about 0.8. And here's the picture in the multiple reserve case. It also worked incredibly well. So we tried 3 algorithms. This is random in the middle. That's our baseline. 2 of the 3 choices worked really well, and we have explanations for why this third one really did not work, but 2 of our choices worked very well. So we were able to find 8 reserve prices here that would really improve revenue in this, I would claim, very complicated setup with a very intense simulation kind of behind the wheel, or under the hood. That's what I want to say, under the hood, a very intense simulation that involves an equilibrium computation. All right, so again, mechanisms are everywhere. Our tax policies, our healthcare systems, everything. We're living in a world of mechanisms. The mechanisms are designed with some objective in mind for the mechanism designer. It could be revenue, as it was for these auctions. It could be the social welfare. It could be, as it might be in the healthcare or the education settings. It could be fairness. If you think about colleges and their admission policies, maybe they want them to be fair in some sense. There are mechanisms everywhere. And what we've been doing is analyzing the design of mechanisms, which is a hard optimization problem, assuming that the behavior by the participating agents is strategic, assuming that they are playing equilibria inside the mechanisms. And we've done this successfully for the advertising exchange environment. We are now thinking about porting it to some of our ideas to the negotiation space. And with that, I have some related work. You can download those references. there are my wonderful collaborators, and I will take questions. Thank you.
Thank you so much, Amy, for your talk. Some questions already came in the chat. I would like everyone to take a quick look at those questions. You can, of course, add more questions if you have them, but please take a look at those questions in the chat and like the ones that you feel I should pass on to Amy. So take a look at the questions in the chat, give the ones a like that you obviously like, and then I will pass them on, the one with the most likes, to Amy. So we will give them a minute here, Amy, to come up with the likes or the questions.
Sure.
And I just need to fill up time by saying that Kingsley said, awesome presentation, with a big smiley. So that's one in. While you are looking at the questions and maybe liking some questions on the list, let me tell you, ladies and gentlemen, that all presentations will be online after the conference, and Amy's slides will also be online after the conference, so you can study them in a more quiet and concentrated environment. I do not see any likes coming in yet, so I'm going to refresh my page here. The system sometimes is a bit slower than you are. The awesome presentation has 2 likes. I will go to a question with 6 likes, Amy, and I will read it out. It's a question by Hassan. He says, when talking about simulators, the first question that comes to mind regards their ability to reflect the real world. How can we measure those simulators' representation of human behavior, which is usually incredibly multivariate and context dependent?
Which is usually, sorry, I missed it. Usually what?
Which is usually incredibly multivariate and context dependent.
Yeah, right. So one thing I should say is that I actually didn't really talk about humans at all. I don't think I said that. But the agents that I was imagining participating in these simulation environments were all autonomous agents, right? WE and WF were algorithms, and we did not have any people or even imagine any people in these current simulations. Now, if you look at the negotiation world, of course, it's full of people, right? So we do need to design mechanisms for people. I think at the end of the day, what we're going to find, for example, think about self-driving cars. What we're going to find is that our mechanisms are going to be populated not just by people, but by agents as well. So we're going to have to think about how people and agents interact with one another. This is not something that I have started to think about. I think other people have. We did a little bit of this. I shouldn't say that. We did do a little bit of this in some of the older trading agent competitions. There were some mixed initiative systems where people and agents could play around together. So there's a little bit of that, but it's not what I was referring to here. So the question of how to model human behavior, I mean, that's not my discipline, but that's not an easy question, right? So, you know, I don't know, there's popular science books about it. For example, my sister for my birthday just gave me the Undoing Project, right? This is talking about human behavior and how irrational it might be. I think maybe that's what you're getting at, is that in my experiments, in my simulations here, I'm assuming rational behavior because I have these kind of idealized agents. And probably the agents that participate in these mechanisms will not be so idealized, right? They might be bounded rational just by computational limitations, but they might also involve people that are doing some unusual things. So in my own research, I do have some work that I've been doing in inverse reinforcement learning. So in inverse reinforcement learning, the setup is that you have a bunch of trajectories of behaviors, and you have to infer what were the motivations, what was the driving force behind those behaviors. So what I've been trying to do in particular, because I'm interested in games, is I've been looking at inverse reinforcement learning in kind of game settings. So you might have 2 learners kind of playing a game together and trying to you know, get to an equilibrium, but at the same time learn what the other agent is interested in doing or what their motivations are. We've been looking at a game where there are multiple equilibria, and one of them is basically to go left and one of them is to go right. And so, you know, maybe one of the maybe there's a preference on the side of one agent or another. And so the other agent is trying to learn, one agent is trying to learn the preference of the other agent. So you're trying to kind of back out what their motivations are. So if we could make something like that work, it could work very generally to say that, if a person is not fully rational, we still might be able to learn some kind of objective function which would explain their behavior in rational terms, maybe. So I think the idea of trying to really model humans is a very complicated question, definitely outside the scope of what I usually think about. I stick to this kind of idealized rational assumption, but I guess we do have in this work I just mentioned the possibility of sort of justifying your behavior as rational or as maximizing some objective that might not be your objective. You might be maximizing something else not very well, but we can sort of reformulate that as here's some actual objective you were maximizing that matches the behavior that we're seeing. I'm not sure if that answers the question. Please feel free to follow up. I should say, anybody can email me anytime. If you're out there and have seen this talk and have direct questions you want to ask me, please do. So if I didn't quite answer the question, please feel free to email me. Here's my email right here.
And this might also be an interesting topic for roundtables later on, or maybe when we go back to the networking area. This might be an interesting topic. I have two more questions that have 4 likes, so I want to see if we can do them both. I'm going to start with a question by Juk, and he says, "How do you evaluate a mechanism?"
Okay, very good. How do you evaluate a mechanism? Yeah, so you have some objective for the mechanism, but of course you don't know the best solution. So what you see, for example, in these plots here is we have on the y-axis the running maximal revenue. So what we're looking at is as we search more and more reserve prices. So here we're searching vectors of reserve prices, so 8 reserve prices every time. As we search more and more, we're looking at how the revenue, the best seen, this is the best revenue seen yet, how the best one seen yet has been increasing, right? And so we might search this many and decide, okay, we can stop somewhere over here, but maybe at 50 we stop, we've searched enough and it's very expensive to keep searching and we're not increasing by that much more, something like this. So we're evaluating this mechanism in terms of its revenue. So mechanisms will have an objective. Like the school choice mechanism had an objective to increase student learning outcomes. And the way you evaluate that is through testing, or that's the way it's generally evaluated. Maybe that's not the best way to evaluate it, but there's lots of testing in attempt to evaluate it. So you have some objective and you figure out some metric, some way to measure how close you are to optimizing your objective. Does that answer the question?
Yes, I think so. Thank you. And the other one with the most likes was one by Alex. And his question is, how might you account for negative externalities, like costs that fall on entities other than the players in these models?
Yeah, negative externalities. They are our nemesis, aren't they? Yeah, that's an excellent question. Let me think.
And now for the excellent answer.
Right. Stay tuned. Coming soon. Right. Yeah, so let's make sure that everybody knows what negative externalities are, for starters. Where we're seeing negative externalities most prevalently is in the environment, right? So, we buy very cheap goods produced, in factories that can produce these things very inexpensively because they are not charged the impact, the cost that they're imposing on the environment. They just dump their toxic waste wherever they dump their toxic waste, and that was free, or maybe they paid a little bit for it, but they certainly did not pay the cost that it's, of the birds and the bees and so on that are suffering from this. They're not paying anywhere near that amount. So they're imposing a negative externality, and they're not seeing the cost there. I guess the answer to the question could be as simple as adjusting the mechanism to really address those costs. So what's coming to mind is a problem I studied in my PhD thesis, which is called the El Farol bar problem. This was a problem in Santa Fe, where Brian Arthur, who invented the problem, lived. He was at the Santa Fe Institute. He will still be there. In this problem, there was a bar with a limited capacity. The capacity of the bar was like 60, and there were 100 people that that wanted to go to the bar every Tuesday night or whichever night that there was some jazz musician coming out to play. But Brian Arthur really didn't like to go to the bar when there were like more than 60 people. It was crowded, it was uncomfortable, he didn't want to be there. So you had a game that you had to play, which you had to kind of predict how many people you think are going this Tuesday. And then you would kind of go if you thought it was going to be fewer than 60, but it was going to be more than 60, you were going to be kind of scrunched and unhappy and uncomfortable and you didn't want to go. So that was the game. And how do you limit the number of people who go to the bar? I mean, the way you can do it is you can basically, it's a little bit like an externality here, kind of if you're the 61st person that arrives at the bar, then you all of a sudden made everybody else unhappy, right? And so you could imagine, this is kind of analogous, you could sort of imagine taxing or charging an entry fee, right, to get into the bar. And so you could try to find the equilibrium by adjusting, you know, adding some costs here on to model the impact, the negative impact that you're having on other people by showing up at the bar. Now, if you're a popular person, you might be wanted at the bar. You might also have a positive externality, right? Like maybe everybody would love for you to be at the bar. That's a positive thing. But I don't know, the average person, maybe they just make the bar more crowded and they would have to pay the cost, the negative externality there. So we modeled that by imposing costs on getting into the bar to try to equilibrate, to sort of make things land around 60 coming to the bar every Tuesday night. So similarly, I can imagine that you would have to adjust the objective of the mechanism to incorporate the negative externalities, and you would have to make sure to charge people for the negative impact that they're having on others. And that's something that we really have not done very well in terms of the environment, and that's the situation that we find ourselves in right now, because we kind of failed in this regard. But if we are more, I think is a great question, and I'm glad I was asked it, because I should be thinking about it more as I go forward in my research to make sure that in any circumstances where I can anticipate that there will be negative externalities, I should be making sure to analyze mechanisms that make sure to charge people for the negative externalities that they're imposing on other people. Okay. Or agents. Yeah.
Thank you. By the way, I think that Corona or COVID solved the whole problem with people being in bars on Tuesday evening. Right. So that problem is off the planet right now.
I forgot to mention COVID. I mean, COVID is another great example where we have mechanisms, right? So we had to think about lockdown. Lockdown is a mechanism. Yeah. And I was having a conversation with a friend of mine who's an infectious disease specialist. You know, maybe we could let the 25-year-old people go out to bars and enjoy themselves. Maybe that's not going to be so dangerous for the population. I asked that question in April. That seemed proving not to be true. But anyway, I asked the question in April, maybe we could do this. But his response was a mechanism design type response. His response was, no, we can't do it because we need a clear policy. We need a policy that people know how to follow, that they can immediately follow. We can't have a wishy-washy, if this, then that, if this, then that type policy. It's too confusing. It won't be enforceable. And so we need something that's clear and direct. Basically, we need the simplest mechanism that we know we can use to contain this disease, even if it's suboptimal. And suboptimal, you know, assuming everybody would just be behaving exactly, you know, exactly as they should be behaving. So that was a really interesting conversation because he was thinking about the game theory when he was talking about what the best policies would be to contain COVID.
Okay. And ladies and gentlemen, thank you. Amy Greenwald.
Thank you.